Hello everyone. In the second chapter, we are going to study the boundary value problems in rectangular coordinates. First section is the partial differential equations. Second is the heat equations. Third section is the wave equations. Fourth section is the Laplace equations. Fifth section is the non-homogeneous boundary value problems. Last section is higher dimensional problems. We'd like to start to define the partial differential equation. First section is a partial differential equations. A partial differential equations contains partial derivatives. In this section, we are going to concentrate on linear second-order partial differential equations. Linear means equation does not have product of a partial derivative of a function and the function itself. Second order means the highest order of derivatives is a second order. In general, the form of the differential equation is expressed this one. Capital A, second derivative of u with respect to x plus second derivative of u with respect to x and y. And c times second derivative of u with respect to y plus first derivative of the round u round x plus round u round y plus u equal g. When the g right hand side is equal to the 0, we call that equation is a homogeneous differential equation. The example is a second derivative of u with respect to x plus second derivative of u with respect to y equals 0. This is a homogeneous differential equation because the right hand side is 0. If the g is not 0, we call the non-homogeneous partial differential equation. Example is the first derivative of u with respect to x plus first derivative of u with respect to y equal y. So g is not 0. So this equation is a non-homogeneous partial differential equation. To solve the partial differential equation, we use the method of the separation of variables. Method of the separation of variables, we consider the solution of the u is expressed the product of the two functions. Capital X is a function of the x alone, while capital Y is a function of the y alone. Then we have a following partial derivatives. First derivative of the u with respect to x. Capital Y is not a function of x. We only consider the derivative of the capital X with respect to x. So we write that this is a x primes. So partial derivative of u with respect to x becomes x prime y. And the first derivative of u with respect to y, we do the same. So capital Y is a function of y alone. So we consider capital Y dy dy. So this is expressed y primes. So partial derivative with respect to y is expressed capital X and capital Y primes. We do the same for the second derivatives. Second derivative of u with respect to x becomes x2 prime y. And second derivative of u with respect to y is expressed xy2 primes. I showed how to solve the partial differential equations in practice. And we need to classify the equation. Second order partial differential equations is classified depending on the value of the b squared minus 4ac. If the b squared minus 4ac is a positive quantity, the equation is called a hyperbolic equation. If the b squared minus 4ac is equal to the 0, we call the parabolic partial differential equations. If the b squared minus 4ac is a negative quantity, equation becomes an elliptic equation. For example, if you consider this equation, second derivative of u with respect to x minus round u round y equals 0. So in this case, a is 1, b equal 0, c equal 0. So this b squared is 0, and then 4ac is this 0. So equation becomes 0. So we call that this equation, given equation, is a parabolic equation because it corresponds to this case. Okay, depending on the type of the equation, we apply the different method to solve the partial differential equations. Final topic in this section is the boundary conditions. On a boundary, one of the following conditions is specified. First case is the Dirichlet conditions. On the boundaries, the value of u is specified. This is the Dirichlet conditions. Second case is the Neumann conditions. The value of the derivative of the round u with respect to n is specified. So if you consider the boundary, this is the boundary. Round u round n means is a normal derivative of u on the boundary. So value of the round u round n is specified. We call the Neumann conditions for the boundary condition. Last case is a sum of the first and second conditions, Robin condition. Value of the round u round n plus h u is specified. H is a constant values. When we solve the partial differential equations, always boundary conditions have to be specified. This is the end of the first session.